So we just proved that if we have an abstract arithmetic operation box, which is a continuous operation, at least at a, b, defined on the complex numbers, then the limit of a combination via box of two functions is the combination of the limits. And this is a nice limit law. This is an abstract version of a limit law where box is meant to represent plus or minus or times or divided by. Now, our real agenda is to have limit laws for the specific arithmetic operations, plus, times, divide, etc. So are we done? Does it follow that these limit laws are all true for all of these things? Well, almost. Um, what remains to be done? I mean, box could be plus, box could be minus, it could be times, it could be divided by. What remains to be done is that this thing requires box to be continuous at the input a, b. And so in order for this abstract version to actually knock down all of these, we need to show that plus itself and minus itself and times and divided by are continuous functions on C cross C. And then we will have these limit laws by the application of this general principle. Now, technically, I don't have to do number one because in a previous video I did number one, but I did it directly. And I want to illustrate the power of this method. And so I'm going to make number one derive from this instead by proving that plus is continuous. This is a pretty straightforward proof. So we're going to prove, we're going to establish here that plus is a continuous operation on C cross C. So so goal here is to prove that plus, which of course is an operation from C cross C to C, is continuous. And it's continuous at every input, but we're going to choose a particular input. So let's let A be in C cross C, and we'll prove that plus is continuous at the input AB. Okay, so continuity, what does continuity mean? So continuity at AB, it means that for every epsilon I want, for every positive epsilon, then I can choose a neighborhood of AB. Now, we could use the metric definition of this, but the simplest thing to do is to choose a neighborhood so that it's a rectangular neighborhood of AB. So basically what I need here is I need a pair delta 1, delta 2, so that for every xy in C cross C, if x is in the ball centered at A of radius delta 1, and y is in the ball centered at B of radius delta 2, then x comma y, then x plus y will be in the ball centered at A of radius epsilon. So to illustrate here, this is going to be kind of a fake picture of C cross C. Technically, C cross C would need four dimensions for me to draw it properly, so I'm not going to be able to do that. But here's A comma B, and then the plus operation maps this to some A plus B. I'm trying to prescribe a neighborhood here, an epsilon neighborhood of A plus B, so that if I make the right choices of delta 1 and delta 2, then I can produce a ball in this direction and a ball in this direction, so that everything in the cross product of these balls is going to have a sum which it lands in this epsilon neighborhood over here. So basically, if x is close enough to A and y is close enough to B, then x plus y will be as close as prescribed to, I did that wrong, A plus B. So how are we going to prove this? Well, addition is very simple, and because of the triangle inequality, it's pretty easy to predict how big the delta 1 and the delta 2 are allowed to be. And in this example, it will work just fine if we choose both of them to be epsilon over 2. So we're going to choose delta 1 to be epsilon over 2 and delta 2 to be epsilon over 2. And then if the distance between x and A is less than epsilon over 2, and if furthermore the distance between y and B is less than epsilon over 2, then let's calculate the distance between x plus y and A plus B. So x plus y distance to a plus b is, of course, the distance from x to a. Well, let me do this in 2 steps. That's x minus a plus y minus b, which can be split x minus a plus y minus b. That's the application of the triangle inequality right there, which means this should be less than or equal to. So the distance between x plus y and a plus b is equal to this quantity, which can be no more than the distance from x to a plus the distance from y to b, which is bounded by epsilon over 2 plus epsilon over 2, which of course is epsilon. And that proves that x plus y and a plus b are no farther than epsilon apart, which establishes continuity of addition. So thus, plus is continuous. Now, how is that relevant in context? In context, that means plus is continuous at every point a comma b. And so this basic principle will apply if if plus is playing the role of box here. And that means that this limit law is generically true for functions to the complex plane. The next limit law that we'll have to do is minus. The subtraction limit law. I'm going to skip it because it's basically the same thing. If you change the right pluses to minuses, then you'll be fine here, and this will establish the same thing. We'll also have to prove the continuity of multiplication and the continuity of division. And when we get to division, then we'll have to be careful because obviously it's not going to be defined or continuous when g of x is 0. So we'll do those next, and then we'll have all of the limit laws for the arithmetic operations as applied to combinations of complex functions.